Now we have seen how we can derive the state diagram from the operations. Now let's see how the digital system, the examples that we have done, can be weaved or demonstrated through the timing waveforms. Now we have got all the inputs and the outputs over here. The clock, subtract, and start are the external inputs, control inputs that we already have defined over here. And the reset, load R2, load R1, add, subtract those are the outputs that the control unit is generating. Data it can be any value that will be fed into the data path. R2 output, the register to output, other subtractor output. So whenever the operation is performed, it will appear over here, and R1 output is going to be the data out. Now, when we are in state 0, where the reset is 1, as you can see, reset is already high, and nothing is going through at the moment, and we are just initializing the system. Now, next thing that we are going to look at, we'll set the control inputs that are feeding into the control unit and the data that we are going to feed into the data path. And before we start running the clock, we know how these operations are going to be performed. Now, reset is 1 over here, and whenever the start is asserted, that means we are going to go into state 1, and reset will be deasserted. And load R2 will be asserted. So load R2 will be 1, load R1 will be 0, add subtract will be 0, and R2 output will have the value of A in there. So we can see that on the rising edge of the clock, reset still 1, after a while it goes down, and start is 1, R2, whenever the reset goes down, load R2 is going to be 1, and we are ready to receive the data. So load R1 add subtract is 0, and we have got the operation as 0 plus 0 because there are no values in there. So when load R2 is asserted, and on the next clock edge, the new data will be loaded in. So load R2 is asserted, and as you can see, now R2 will have the value of A, data in. Okay, so we are in S1, it's completed, and in S2, we have got data in. And as R1 is also asserted, other subtractor will have the A plus 0, so the R1 value. Okay, so A plus 0 will give us A, and that will be stored in the next clock edge in R1. So as you can see, R1 has got the value of A, R2 has got the new value, which is B, and it's deasserted, R1 is still 1, and as start is asserted and subtract is 0, we are going to perform A plus B operation. So on the next clock edge, as you can see, A plus B is performed, and the value will be stored in R1. Now everything is going fine up until now, and we keep at R1, R2, R1, R2, and so on. Now, over here, start is deasserted. So when the next clock edge comes in, everything is going to go back to the reset, and it will reset the registers. So reset will go high as well, and start is deasserted. Load R1, load R2 are 0, so the register values over here are going to be zeros. Okay, so we go back to S0 and then S1. And we are ready to load new data, which is C, first into R2. So reset goes down, R2, load R2 will be asserted, start is 1, and subtract is also 1. So New value will be loaded into R2 and C plus 0. Now R1 is asserted, so C will be stored in R1. And then as we are doing subtract operation, it's going to perform C minus D and it will store in R1. So we have got C minus D and it will be stored in R1, which is state 5. So this is how we can go through step by step with the timing waveform to demonstrate the state diagram and show the operation of the digital system. Okay, next thing that we do in chapter 5, it was after the state diagram, we have to derive the state table so that we can identify how the states are going to interact with each other, and we can derive the flip-flop inputs and implement the sequential circuits, because control unit is actually made up of a sequence of steps, which we can perform them using sequential circuits. So I'll just have the state diagram over here because I want to write. Now what we need to take care, we have got 6 states, S0 to S5. So I can say over here, present S0, S1, S2, S3, S4, and S5. Now, the next states that we are going to have, it has to be dependent on the external inputs that are coming in. So what are those external inputs? Start and subtract. So what do we have? We have got start, maybe a little bit higher, start and subtract. When their start is 0, where we don't care about the subtract, we can put don't care. So let's put it 0 and x. Then we also have, again, start and subtract, where start is 1, subtract is 0, so it goes for the addition. And alternative, start, subtract, where start is 1, subtract is 1. And that's all. And we also have the outputs. Now, what do we have in the outputs? We have got the control signals. So add and subtract, load R2, load R1. I cannot fit everything here, but that should be R1 and reset and so on. Okay. Now, we have got the next states and we have got the present states, and for each of those, we have to think about how they are going to be derived. Now, when we are in S0, over here, start is deasserted, so we don't care about add and subtract. It will be staying at S0. And when we are in S1, or let's say S0, start is 1, that means it has to jump to S1. And start is 1, subtract is 1, again it's S1. And the output pattern, so based on this, it's going to be 0, 0, 0, 1. So the first line, done. The second line, when we are in state 1, if start is deasserted, it goes back to S0. If start is 1, it goes to S2. No matter what the operation is, the next step is S2. and the output is 0100. Then, when we are in S2, if the start is deasserted, we go back to S0 again. When the start is asserted, we have two alternatives. Either subtract is 0, which goes to S3, or subtract is 1, which goes to S4. So we can have the output as 0110. Then, when we are in S3, if start is deasserted, in S3 it will go back to S0, and if start is 1, we go to S5, and if start is 1 and there is a subtract, then it has to go to S5 as well, because we have to reset and go back to S4. So we cannot go directly over there. And the output over there is 0010. Then when we are in S4, if the start is deasserted, it goes to S0. And when start is 1, it goes to S5, S5, and then the output is 1010. And when we are in S5, if the start is deasserted, it goes back to S0. If start is 1, we just wait in S5, wait in S5, and the output is 0000. So we have got all the states. Now, when we think about it, if you want to generate these flip-flop implementation, if you want to implement it using flip-flops, now we have to think about the number of flip-flops that we are going to use and how many gates we are going to need it. Now, if I go further, now this is the outputs that we have got with the table over here. So when we consider this ordinary binary assignment or a gray code or something like that, now how many flip-flops do we need over there? And how many maps do we need to generate in order to simplify it is important. So if we are using ordinary assignment or a gray code, we need 5 variable, 3 variable, and 4 3-variable k-maps to derive optimized logic in sum of product form. Now, this is quite complicated and it will take ages to implement it or optimize it. Now, alternative is, again, using one hot state assignment. So, one hot state assignment, okay, maybe here we just use 3 flip-flops, but optimizing it to get the circuitry, it will be really difficult. But if we use one hot state assignment, we will have 6 flip-flops. One flip-flop will be activated at a time, like the decoders, and we do one hot state assignment. So S0 is 0001, where flip-flop F is activated. S1 is 00010, where flip-flop E will be activated. S2 is 00100, where flip-flop D will be activated, and it goes like that. So it's easier and we can implement it without using any k-maps. So let's see how are we going to derive those. Maybe I can write it over here. Okay. So if we start with S0, where we can say, or let's say we want to start defining the flip-flop A, because what we know is A plus is actually going to be equals to DA. Okay, so that value, so where A is activated, which is 10000. So where do we have got that one? We have got it over here and here. All these 6 places, which we have got S5s. Okay, so S5, A is activated. Now, when you think about it, 3 rows, A, B, C. So A, B, C is activated in these 3 rows, and start is always 1, subtract is changing. So all I can say is start is 1. Let's use the common colors, the color coding. So A plus DA. So start is 1 in both cases. Okay, for S5 or flip-flop A, and we have got A or B or C. So I can say start A or B or C. Then flip-flop B, which is state S4. So flip-flop B is activated where we have got 0, 1, 0, 0, 0. Now there's only one place that we have got 0, 1, 0, 0, 0. This is where D is activated. And where start is 1, subtract is 1. So we can say this is start and subtract and flip-flop D. Okay? So start, subtract, and flip-flop D. Then flip-flop C, which is 0, 0, 1, 0. So 0, 0, 1, 0 is actually happening over here. Okay, so where we have got again D is activated and we have got start and subtract inverse. So start, subtract inverse, and it's going to be D again. So C plus is done, then D plus. Now we are looking at here 0, 0, 0, 1, 0, 0. 0, 0, 0, 1, 0, 0 is here on those two, where we have got start, subtract is changing, and E is activated. Okay, so start and E is activated. So D is start and E. And then we have got E plus, which is 0, 0, 0, 1, 0. 0, 0, 0, 1, 0 are those 2 points. Start is 1 and it is F. So start and F. And the last one is F next state. So F is 0, 0, 0, 1, which is all of those where start is 0. So we can just say start and all of those, so you don't need to write it at all. When the start is deasserted, it's flip-flop F. Okay, so this is how we can derive the flip-flop inputs equations, and we can use these in order to implement using D-type flip-flops. All you just need to do is use these inputs and connect them up together. We can also use the same approach for the outputs. So for example, add and subtract is only activated at this point, okay, at this column. So where we have got B is activated, so add and subtract is going to be B. Then L2 is activated on those 2 lines. So those 2 lines are DE, okay? So D or E for load R2. And load R1 are those 3 lines. So either it's B or C or D. So B or C or D. That's why load R1 is B or C or D. And reset is only activated for F. So we can have those output expressions as well, which we can use it to implement the circuitry. So data path is designed by identifying the temporized trace registers required in the digital system and coming up with the combinational logic between the consecutive registers to enable data processing. We have seen it from the diagram that we have registers, arithmetic operators, maybe a multiplexer or a decoder inside of a data path. And the nature and the size of the temporary storage and combinational logic depends on the performance, power, size, cost, and some other design constraints. And it's also dependent on the architecture, if it can only be 8-bit or 16-bit or something like that. And register transfer operations or micro operations, they actually provide information on the data path, which we have seen it, and then we have derived the state diagram based on that. Okay, so that's all I want to say about this chapter, FSMs. There are 5 exercises at the end of this chapter, which we are going to solve them in the live session. Thank you.